All right, hello everyone. So this week we're going to get started with a new chapter. We're kicking off Unit 3 here, and this chapter is going to be carboxylic acids and their derivatives. Before we get into what a carboxylic acid derivative is, let's just focus on carboxylic acids for a second. We know a lot about carboxylic acids from the first semester when we did the acid-base chapter. I mean, importantly, we know how they behave as acids. But of course, when we're introducing a new functional group, the first thing we need to do is talk about nomenclature, so we can actually talk about this. Carboxylic acids have the suffix oic acid. Okay, so for example, in this molecule here, we have 1, 2, 3, 4 carbons in the parent chain. All right, so for 4-carbon alkane would be butane. This now becomes butanoic acid. Okay, so you just stick that suffix on, a lot like aldehydes. One of the convenient things about carboxylic acids is that they always have to be located on a terminal carbon. So they're always going to be located at position 1 on carbon 1. So we'll start counting from there. Let's do this next example, but notice that this has an alcohol group in there as well. So we need to take a look at this priority chart real quick before we can actually name this compound. We're going to be talking a lot about carboxylic acid derivatives. That would be like esters, acyl halides, amides, nitriles, but we will get to all of that. So for now, we're going to go ahead and ignore this portion of the chart. We'll cross that bridge when we get there. But notice that carboxylic acids are now our highest priority functional group. Okay. When we started the semester, we were over here at alcohols, and then we added some more functional groups. Carboxylic acids are the highest priority functional group we're going to learn about in this course, actually, which are a lower priority group. So instead of referring to that alcohol group with the ol suffix, we're going to use the hydroxy prefix. Okay, so let's go back to this example here. Besides that, the nomenclature is just like always, right? I'm going to find my parent chain. So I'm going to start here, 2, 3, 4, 5. So then I have my hydroxy is at position 5. Oh, and again, importantly, I'm going to start numbering from that carboxylic acid carbon. Okay, so this would be 5 hydroxy, 4,4-dimethyl pentanoic acid. Okay, so again, keep this priority list in mind. We'll cross the, that reds or the green stuff that I crossed off. We'll get there when we get there. Carboxylic acid. So the next thing we need to talk about with nomenclature would be, this is kind of a special case, but we do need to learn about it, is what happens when the carboxylic acid is branching off of a ring. The reason why this is kind of special is because, of course, it can't be in the middle of the ring, right? Because it's got to be on a terminal carbon. So it's not really a part of the parent chain in that traditional sense. When it is located 1 carbon away, you just name the ring, cyclohexane in this case, and then stick carboxylic acid on the end. So cyclohexane carboxylic acid, cyclopentane carboxylic acid, cyclobutane carboxylic acid. Those are all ring structures where the carboxylic acid group is located just 1 carbon off. There are also a lot of common names for carboxylic acids. Carboxylic acids are incredibly important in organic chemistry and biochemistry. So they have a lot of common names. I'm going to leave these in this slide because Wiley is going to want you to know them. I'm not going to make you guys memorize them. I'm going to focus way more on the IUPAC naming scheme and making sure that you know how to, generate the name of any miscellaneous compound you're given. I'm not big on memorizing common names. Got to be one exception though, and that is the all-important acetic acid. Okay, this, right? If we're going to be systematic, there are 1, 2 carbons. So this is ethanoic acid. You will literally never see ethanoic acid anywhere. It has acetic acid is just so important. such a deeply enrooted common name. I bet it's actually officially the IUPAC name, despite the fact that it doesn't have that same sort of whatever. So anytime you're about to write ethanoic acid, you instead put acetic. Okay, ethanoic doesn't exist, replace it with acetic. Okay, there are some other ones, formic acid, propionic. Notice how this is not propanoic, but the common name is propionic. This is not butanoic, the common name is butyric acid. I have no idea why. They're very commonly used. For the purposes of our course, we're going to stick to the IUPAC, the propanoic, butanoic, again, with the exception of acetic acid. We just got to know because that is just so commonly ingrained. Dioic acids or dicarboxylic acids. So kind of what we would expect, right? Similar to aldehydes. Again, they both have to be at the terminal end. So we don't actually have to like specify the location. We just have to 1, 2, 3, 4, 5. Figure out how many carbons we have in our parent chain. Again, this would be, instead of just pentandioic acid, it's pentane dioic acid. The real reason they do this is so that you don't have two consonants sticking next to each other. So you just stick that E on there as well. So this is pentane dioic acid. And again, notice that we don't have to specify locations because we know they're just going to be on either end of this parent chain. Again, some dicarboxylic acids have common names. I'm not going to expect you to have them memorized, but I want to keep them here in the lecture notes for when it comes time to the Wiley Plus homework. Okay. Properties of carboxylic acids. So of course, just like ketones and aldehydes, that carbonyl carbon is sp2 hybridized, which means that those carboxylic acid groups are flat, they're trigonal planar. Carboxylic acids are capable of very strong hydrogen bonding. Each carboxylic acid group has both a hydrogen bonding donor, a hydrogen that can be sort of participating in hydrogen bonding, as well as an acceptor on an electronegative atom. So because of that, they have very strong intermolecular interactions, and we expect carboxylic acids to have even higher boiling points than alcohols. One of the first reactions we ever learned about in this course, and we should be well aware of, is an acid-base reaction, right? So this is the simplest reaction you can have with a carboxylic acid. That is just your base acting as the nucleophile doing a proton transfer, and that pair of electrons jumping onto that oxygen. This creates what's called a carboxylate salt. One of the big confusions is people, like, when they see something like this, they assume that sodium is reacting with oxygen or something like that. When you carry this acid-base reaction out in solution, this thing is very much so soluble. Those ions will be floating around separately. It's not until you evaporate all this water, get rid of that, that those two counter ions will find each other, and then you'll be left with a solid. Carboxylate salts can be easy to deal with, right? Ionic compounds are usually solids, which means that they're easy to pack or, to transit and to mass out and all that good stuff. So there are some reasons why we might choose to work with the carboxylate salt version versus the acid version. Of course, we could always go back the other way by just adding some proton source. In terms of naming them, carboxylate salt, you replace the ic acid portion with oate. Okay, so benzoate. Propanoate would be the, I guess we need 3 carbons. Sodium propanoate, okay? Now let's talk about pKa's, right? Because that's, carboxylic acids, it's in the name, it's an acid, right? So now let's talk about its acidic properties. Carboxylic acids tend to have pKa's in the 4 to 5 range. That means that they're not crazy acidic. Certainly wouldn't be too terribly worried if we spilt some of it on our hands or something like that, but they often will play the role of a proton donor in a reaction. So the sort of go-to reference would be your acetic acid or maybe your propanoic acid, and they have pKa's of around 4.8. And then there are various things that we can do that will increase or decrease the acidity relative to this kind of baseline here. So we add a benzene ring on there. We sort of have learned that benzene rings kind of act as electron withdrawers. Remember that what's going to make an acid stronger is stabilizing that conjugate base even more. So that's what benzene will do. Helps stabilize the conjugate base, that carboxylate ion, and thus increase the acidity or decrease the pKa. So again, compared to like what we think about as strong acids, hydrochloric acid, sulfuric acid, carboxylic acids are relatively weak, right? Both of those have pKa's in the negatives. Carboxylic acids, again, are like at the 4 to 5 range. But if we're going to compare to alcohols, then they're relatively acidic, right? So it's all sort of a game of relativity. Nonetheless, we're going to see them donating protons a ton in our reaction mechanisms. What makes them so much better than an alcohol is simply that resonance stabilization that you have of that negative charge, right? So the presence of that other oxygen means that you have these two resonance structures helping to stabilize that negative charge. Anything that increases the stability of the conjugate base will increase the acidity. Other things that we can do to, again, stabilize the conjugate base is by putting an electron withdrawing group on that neighboring carbon, right? And look, the more the merrier, right? So 1 chlorine will drop the pKa quite considerably. If I have 3 chlorines on there, now I'm on the level of like a really strong acid. Okay, so, and all these are doing is stabilizing that carboxylate ion. Also notice that proximity has a lot to do with it. If the chlorine is right next to it, again, my pKa is now around 3. I move it 1 carbon away up to 4, 2 carbons away up to 4.5, pretty close to that now 4.8 baseline. Talking about benzoic acid derivatives. So look, notice here, this is if there was a hydrogen in this position here. Benzoic acid, again, has slightly lower pKa than acetic acid, 4.2. And what do we know about these groups over here, right? So these are all electron withdrawing groups. Notice, remember this nitro group we would call the strong deactivator, strong electron withdrawing group. The aldehyde was moderate and the halogen was weak. And notice that it has sort of a effect on the pKa that corresponds with that, right? So again, this is all about these electron withdrawing groups through the ring are able to pull electron density onto themselves, further stabilizing that carboxylate ion. And the exact opposite is true for Re donating groups, right? If we go to all the way over to the alcohol, that is a strong electron donating group. So this will have the effect of slightly destabilizing that carboxylate ion relative again to the baseline of if that was just a hydrogen. Okay, so now let's talk about reactions that we learned about in the first and second semester that will generate carboxylic acids, right? Preparation of carboxylic acids. The first one that we learned about was actually how to turn an alkyne into a carboxylic acid using an ozonolysis reaction, right? Alkenes will undergo ozonolysis to either aldehydes or ketones. Alkynes will undergo ozonolysis all the way to carboxylic acids. We can also use oxidation agents, right? So if we had a primary alcohol or an aldehyde, we could oxidize that with one of our strong oxidizing agents. Again, this chromium is the giveaway for a strong oxidizing agent, and that will generate a carboxylic acid. And then in our benzene, I don't remember what it was. One of those chapters where it involved benzene, we learned about reactions at the benzylic position, which is that you can actually oxidize that 1 carbon removed to generate a carboxylic acid, kind of chopping off these other carbons. Okay, so these were past reactions that will generate carboxylic acids. Another one that we actually did talk about last chapter, but worth going over again, is that we can take a nitrile group, this cyano group here, And just by using acid and heat, that will actually oxidize all the way, or I guess it's hydrolyze, all the way to a carboxylic acid. So this is now another way that we can transform one functional group into a carboxylic acid. And we can generate these cyano groups or these nitrile groups by taking our alkyl halides, especially if it's a primary alkyl halide, because this will be an SN2 reaction, and put on that cyano group. Again, then just hit that with heat and acid, and that will hydrolyze to a carboxylic acid group. In terms of like how to spot whether or not this occurred in a synthesis problem, look how we jumped, we added exactly one carbon. Another method is using a Grignard, which we talked a lot about, right? So this is this now, BR, MGR. It drives me nuts that the book does not include the MG and BR in there, but I didn't write the textbook, so it is what it is. We know that these will react with aldehydes and ketones by attacking nucleophilic attack on that carbonyl carbon. Well, carbon dioxide also has a carbonyl carbon, right? And so we can see the exact same thing, nucleophilic attack on that carbonyl carbon, that has to kick one pair of electrons up. But now, unlike before, we actually have two oxygens on that carbon. We can then just protonate that by this acidic workup and then generate our carboxylic acid, okay? And again, just like before with our cyano group, we've added exactly one carbon onto our chain that contains that carboxylic acid group. So if we're going to start with an alkyl halide, again, whether we went the route of the cyano, adding the cyano group and then hydrolyzing that, or creating a Grignard and this is now an ether solvent, that's not actually playing any significant role, and then reacting it with CO2. This one wouldn't be, you couldn't do the cyano group on this one because it's directly attached to the ring, my bad. Nonetheless, both of these methods will add one carbon that has a carboxylic acid group on there. We can reduce a carboxylic acid using lithium aluminum hydride. Okay, so we've talked a lot about a lithium aluminum hydride and how that will reduce things all the way to alcohols. Turns out carboxylic acids are no exception. What is weird about them is the mechanism in which it happens. Usually the first step is that hydrogen acting as a nucleophile attacking the carbonyl carbon. Here it actually pulls off a hydrogen, that acidic hydrogen, forming a carboxylate ion. The next step is, we can't now, the interesting thing is that we can't now, if we start with this carboxylate ion, we can't have nucleophilic attack on that carbon because of that negative charge. It means that that carbon is no longer nucleophilic. So what is believed to happen is that the oxygen actually interacts with the aluminum hydride to create an aldehyde. Now that we have an aldehyde, we can have our normal old reaction mechanism where hydrogen acts as the nucleophile, carbonyl carbon is the electrophile, kicks that pair of electrons up. We're now stuck with this oxygen with the negative charge, so that has to be pulled from either water or an acidic source in order to generate our alcohol, okay? I'm actually not going to make you guys memorize the reaction mechanism for carboxylic acids and lithium aluminum hydride. We're going to have to for almost every other compound, but this is kind of bizarre. Important though to note that just like every carboxylic acid derivative, as we're going to see, as well as the aldehydes and ketones, lithium aluminum hydride can be used to reduce this functional group to an alcohol. The last one is kind of like a special case designer kind of thing, and that's using borohydride. Just as a reminder, what we're used to seeing borohydride used for, along with a bunch of other stuff, but just to be brief, oh, actually, let me do this, is it's good at putting a hydroxy group on the less highly substituted carbon, right? We had a bunch of ways, or 2 ways for putting alcohol groups on the more highly substituted carbon. The shtick of borohydride, borane is to put it on the less highly substituted carbon. This is actually, so it doesn't do the same thing here with carboxylic acids, so kind of got to keep it in a different place in our mind. It actually plays kind of the same role as lithium aluminum hydride in that it reduces this to an alcohol. The difference is that borane is selective to carboxylic acid groups. So unlike lithium aluminum hydride, which would hit aldehyde and ketone groups, this one will not. It will only reduce that carboxylic acid group. So if we take a compound like this that has mixed functional groups, we have our aldehyde over here and our carboxylic acid over here. If we hit it with our borane in THF, we get only reduction of that carboxylic acid group, okay? As opposed to, right, if we used, let's just to be clear, so if instead, we went the lithium aluminum hydride route, we would also reduce that guy over there, right? So it's just a way of selectively reducing carboxylic acids and not touching other functional groups.